Now that we have our rotations implemented, let's take a look at our insertion code. The idea of the insert is going to be pretty similar to the binary search tree that we saw previously with a few small modifications. The first modification is that I'm actually going to show you an iterative approach to doing an insert into a tree. Previously, I told you that recursion is pretty common for tree-based structures, so I showed you a recursive implementation of the insert. I now want to show you how we would approach an iterative insertion for really two main reasons. The first is that it tends to actually work a bit better in the red-black tree. You'll see that it's because we generally have to track the parent as well as the current node, so iteration just tends to fit a little bit better. And the second reason is just to show you that it's possible, right? I just want to show you that you can also insert iteratively rather than inserting recursively. So I just want to give you a few different options of things that you could do, right? We're going to create a holder that's going to start at the root, and I'm going to create a holder that's going to represent the parent, which we'll call y. And the idea is going to be that we're going to iterate while the actual value x that we started at is not nil, right? Once we reach nil, that's where we're going to insert the value. And basically what we do on each iteration is we set the parent equal to the current node, and then we move the current node forward based on where its value is. If it's less than x dot value, then x equals x dot left. Otherwise, x equals x dot right. And we do that iteration until we reach the end of the tree where we can place our node. Once we reach that point, I'm going to create a new node, which will be a node with the value that we're trying to insert. And I'm going to set its parent equal to y. So those are all the pieces that we need in order to do this insertion. Now, basically what we're going to do is we're going to say if y is self.nil. Basically what that means is that this is the root, right? Like I mentioned in the previous video, if something doesn't have a parent, it must be the root. The root is the only thing that doesn't have a parent inside of our tree. Otherwise, if new node.value is less than the parent's value, well, then we're going to insert it to the left of the parent, right? And then finally, if it's none of those two cases, then we're just going to insert it to the right-hand side. And then as our final piece here, we're going to set new node.left equal to nil. We're going to set new node.right equal to nil. And like I said, when we do insertions, the color that we set our node to is red, right? So we set the node to be the color red. And that's all we really need actually to do a very basic insert. So this would insert a node into our tree. Now the problem is we have to fix the insertion violations. So we still need to do a little bit more work. And generally I would do that in a separate function, which I'll call fix insert. And I pass it the node that I just inserted. It's going to start at that node, and it's going to check for violations up the tree and fix everything that it finds. Let's take a look at how that generally works. Fix insert is going to take in, as I mentioned, the node that we want to start with. And it's going to run while the node's parent color is equal to red. And the reason for this is because if the parent is red, we could see violations in our tree properties. For example, every single red node needs to have black children, right? So if the node is red, we need to check for those potential violations. That's why we're iterating while the color is red. And what we'll see here is basically that we do checks based on the different circumstances I talked about in one of the first videos of the red-black tree section. Basically, if the node's parent is equal to the left-hand parent of the grandparent. So what we're really seeing here is basically, so envision the way that we're inserting our node. We inserted our node similar. That node has a parent. The parent also has a parent just above it, right? We're saying if it's on the left-hand side of its parent, right? So basically it's on the left section of the tree. That's what we're really checking for here. The reason why we're checking for this is because we need to make sure that we do the right rotations on the actual node itself. So we want to make sure that we're on the right portion of the tree. And then what I do is I set y equal to node.parent.parent.right. What is this? This is the uncle of our node's parent, right? So the node that we inserted, its parent's uncle, right? And remember that we're taking a look at that uncle to determine what sort of changes we need to make, right? The first potential change is that if that uncle is red, right? If it's red, we have the first case that we talked about. Basically, what we have to do is we have to recolor the parent to be black. And then we have to recolor the uncle to be black. And then we have to recolor the grandparent to be red. And then what we do is we update the node to be node.parent.parent, so the grandparent. So basically what ends up happening is once we finish fixing this particular section of the tree, we then move up to the next section, which would be at the grandparent. And then we check again. We start looking for more violations, right? So you see that we fix one section, and then we move to the next section, and then we continue doing fixes and checks. So that's the idea of what we're really doing here, right? So that's the first sort of fix that we need. Now, the second case that we have here is what if the uncle isn't red, right? Well, if the uncle isn't red, we have basically the idea of we're going to check to see if the node is equal to node.parent.right. So if it's on the right-hand side of the parent. If it is, we're going to set the node equal to its parent. And then I'm going to do a left rotate of the parent, right? And then what I do here is I do a recolor. So I do a change of the parent color to black. And then I'm going to change the grandparent color to red. Once I've done this, we just want to do one more rotation, which is a right rotate. And we're going to do a right rotation on the grandparent itself, just like this. So those are the main cases that we're covering here. Now, what ends up happening at this point is we have an else statement for this if statement right up here at the top, right? The one that checked if we were on the left-hand side of the tree. So now we want to do things for the right-hand side of the tree. And as I've mentioned, there's a lot of symmetry. What you do is you take this code here, you copy it over, you change right to left, left to right, and you're done. So just remember that there's a lot of symmetry in this. You only have to remember one of the cases, and then all that changes is the left and right pointers. So this left rotate, for instance, is going to become a right rotate. This right rotate becomes a left rotate, and that's all there is to it. I always like to show this because some people will kind of like go over all of this code. It's literally the exact same as this code here. We just change lefts to rights and rights to left because it's symmetric, right? So you could save yourself the time, just memorize or remember these lines of code. Once you remember these lines of code, you just flip the case, you change the lefts to rights, and you're done, right? So it's a nice and easy problem to solve. The final thing that we need to do, no matter what, is we have to update the root color to black. Just to make sure if it were changed at some point, we want to make sure that it always stays as black so we don't violate that condition that the root has to be black, right? And that's all there is to it. So hopefully this helps with understanding the red-black tree. It helps to reduce down some of that intimidation behind it. Since it's such a symmetric data structure, we don't have to really worry about, understanding all of the cases. We just need to understand the first few cases, and then we just flip the lefts and rights, and we're done, right? So nice and easy. Let me actually show you that it works, though, because we want to make sure that we're actually getting a correct tree out of this. So we'll just go ahead and make sure that I haven't made any sort of typos or anything like that. I'm going to show you an insertion that I know would definitely result in an imbalanced tree in previous circumstances. If we were to do this with our first binary search tree, we would end up with that linked list structure. 1 would become the root, and then to the right would be 2, to the right would be 3, right would be 4, and so on and so forth, right? In this circumstance here, I'm expecting that rotations are going to happen. We're going to end up with a more balanced tree. And to demonstrate that, I'm going to show you what the root ends up being, right? So what does the root end up being in this case? In our previous case, we would have seen that the root was going to be essentially 1, right? So let's go ahead and give this a try and see what ends up happening. It's the chapter 8 and node.py. Do you see that the root ends up being 2? So the root has actually changed, right? The root initially would have been 1 since it was the first thing inserted. It got changed to 2. So that's interesting, right? Let's take a look at some of the other values inside of our tree. We can kind of like pseudo-iterate this, right? So we can check to see what's on the left-hand side of this root. We can check to see what's on the right-hand side of this root, right? And we can see what each of those values ends up being, right? So do you see that to the left is 1 and then to the right is 4? And then I could continue going through my tree, right? So I could take a look at the left value, and that ends up being 0, which would actually be a nil node. And then I could take a look at the right value, right? you see that that ends up being 5, so that's where the 5 ended up. So do you see that we actually ended up with basically our whole tree here, right? So we ended up with the root, the left, the right, and then the right dot right, and then the left dot left ended up being a nil node, right? So you could see how this structure is actually being built out inside of this tree, right? Now we can actually do the different iterations to see this in a bit more detail, right? And we'll take a look at that in a future video just to see how we can get our iterations into this tree itself. It's not particularly hard to do, just a few small tweaks to actually make that work. Then we'll also take a look at deletion, so how we actually remove nodes from our tree. So we'll take a look at those two ideas in the next video. So thanks so much for watching, and I'll see you in the next one.